So before that, I'm sure you're a bit bored already. So let's watch some videos. So this is about reconstruction. And this is what we want to get in the end. Yeah. No, there was another problem. It's good. It's good. So the question we're asking is, what can we tell about the 3D object shown in the image from multiple images? So Bishes already showed some example where you had cars being recognized and given boxes. So that's like pattern recognition. You're recognizing cars. And then we had also how far the cars were and what's the geometry of the car. There were 3D bounding boxes there. So meaning that it learned also what's the geometry of the car and what's the shape. So we will talk about the second part, more about how we can recognize the shape of how we can compute the shape of the object from images. And the source main reference I'm using is a book, a very well-known book in the field. It's called Multiple View Geometry, written by Hartley and Zisserman. So everyone who does 3D reads this book once at least. So let's go into what a camera is. So we're using camera every day, and we take pictures and we get pictures, and sometimes we fail to recognize that we're getting 2D information from 3D. Pictures are all 2D. So what happens is you have a 3D object. Sorry. Yeah. You have a 3D object, and the rays from this 3D object is projected onto a plane, not a sphere or not whole surface, but on a plane, and then you get the 2D image of this object. So this is a very classical way to represent camera, and it was actually a camera, a pinhole camera. I don't know if some of you have done this in like physics. Did you create a camera with pinhole model? Did anybody do it? There used to be, like in my school, they had this science fair and things, and they created this kind of camera. So here the image will be inverted on the plane, on this plane, and the image plane creates the image by cutting the rays, right? It slices the rays, and then it creates the image. So this is the model we use for all cameras, even now, by adjusting some parameters. We will see that later, how. So the advantage is that you can cut the plane any location. You can cut it here, you can cut it here, right? To make the model simpler, we always cut the plane at distance 1 from this pinhole. So this is the focal length of the camera, and this is always fixed as 1. So now the thing is that you have the projection here, it's inverted, and it's behind the camera, which is not that convenient to use in real life, in practice. In mathematically, this is same as if you put the image plane in front of the camera. You can just think of a virtual plane that cuts the rays in front of the camera, and then it creates the image here, which is now upright. It's not inverted, now it's upright. So this is a mathematical model of the camera. This is equivalent to the model of the real pinhole model. And this, again, this distance, you can keep it as 1. So what other differences do you see between this and this mathematically? The only difference is that it's the images are now upright; they are not inverted. Right? So this is what a camera projection is: a 3D rays coming into 2D plane, and wherever the plane hits the rays, that's the image of the point. And they are all converging to, the rays have to be converging to this point, which is the camera center. So now let's expand it a bit. Now it's always convenient to model coordinate axis when you are defining cameras and when you're defining projections. So we define the z-axis as the line passing from the center, camera center, perpendicular to the plane. So towards in front of you, if you imagine your eyes are the cameras, so in front of you is the z-axis, and the distance on the z component to any point is your depth in this of the scene. So again, we keep the focal length as 1. So distance from this image plane to the center is 1. Is anyone confused about the model? No. You can do like this if you are confused, or you can make signs so nobody else knows and only I know. The center values C1 and C2 to the UV coordinates, right? So if you add C1, which is the central location, then you change the axis to here. This should be, you can work it out as well. Let's see. Can you check? Is it difficult to see? If you add, let's say you have UV as previous, and you want to change the axis to the top left corner. How do you compute the new coordinates? You need to add this translation, right? This translation, which is C1, C2. And this is represented by this equation. So a lot of things, I think I can give you intuition like how it is, but without working it out, you might not really be convinced that this is true. So shall we go forward? So next change is that the real cameras have lenses, which changes the focal length into, because lenses can converge rays faster. It means that it changes the focal length into much higher value than the pinhole camera. So in real cameras, the focal lengths are much higher than 1. So how does it change the coordinates, the pixel value locations? So if UV was your previous pixel location, what you need to do is, to get a new pixel location, you have to scale it by the focal length, f, for the new, for the UV coordinates of the pinhole camera. So the new So first thing is you have to also scale. At the same time, you also have to add this shifting coordinate system. And then the new equations becomes k times m p equals to q prime, where q prime is your new measured pixel locations, so new coordinate system. And this is the model we use for real cameras, like your smartphones, your laptop cameras or whatever, to compute or to analyze projections. Is anyone confused about the focal length? I think this is trickier than the this shifting coordinate because of C1, C2. Nobody? Okay. So on to the next thing, 2-view geometry. I think you already see why we're doing 2-view geometry now. Because we want to get the 3D of the points. So you already see that before, if we knew that the point Q1 in the image, we knew that the 3D would lie somewhere in this line. So now if you have two cameras with locations you know perfectly, then, and you know that the same 3D point is here, projected here, so the 3D point should also lie on the line of this camera. So you have a solution to the 3D point directly, geometrically. Is everyone okay with this? So what's happening is you have a 3D point here and you have two cameras with the same model as before, and it gets projected into two image planes. And you have Q1 and Q2. So there are a bunch of things happening here. So the study of this kind of geometry is called epipolar geometry, and it's a very specific kind of geometry used to study 3D vision. So what happens is that you have a plane here passing through the two centers and the 3D point. And this plane passes through the point of the projections, right? All right, let's take pictures of Netapola temple. Then you have, let's say, Netapola real there somewhere. Somebody from the left took a picture, and somebody from the right also took a picture. So those 2 points are the same point, same physical point in the temple, and it's getting projected here in these images. So these 2 points are called the corresponding points because they represent the same physical location in the 3D, and they are projected differently in the images. So if you see the pixel locations of Q1 and Q2, on each camera they will be different. They will be at different location. Like you move the camera here, like you will be at different position. So the pixel locations change, but they still represent the same physical point. So that's why they are called corresponding points. So there is what's happening here is that why do we get different views of the same object? Because our camera is being rotated and translated. So although they're identical cameras, they are rotated, translated. So it means that they will observe differently, different views, different points, and they get projected differently. So the first camera is at 0 location. So here we're trying to derive the relationship between these corresponding points, Q1 and Q2. Yes. So Q1 and Q2, is there a relation between them? Or you probably cannot tell anything between those 2 points. So what can you tell about Q1, Q2, and P? Can you tell something geometrically? What do you see?
Excuse me, I would like to make one kind request to all of you while you're thinking about this problem. There's a lot of clicking of pens. I think it's distracting a lot of participants, so I would kindly request not to do that. Thank you.
Okay. So what I wanted to say is that Q1, Q2, P, they form a triangle, which is the same plane as the camera center, this camera center, and P. So what we want to do is we want to derive the relationship. For that, we should assume the camera, how the camera had changed. The first case, the camera is at origin and looking straight. So that was identity and 0. Let's go back. What is identity 0? So this first part, let's see. Yeah, this first part is identity, right? This is the identity matrix. And the second part is 0. And in fact, these two things, the first part represents the rotation of the camera, and the second part represents the translation of the camera. So first part, we have first camera, we have I0, and in the second camera we can represent in the same coordinate axis as first camera by putting RT. So in fact this line is T. It's being translated, and the rotation means that the projection of P will change onto this second camera. So the relationship we can derive by just considering these two vectors. These two vectors highlighted in red. What do you think will be the cross product of these two vectors? Q2 and T. Oh, where? Towards you. Perpendicular.
Outward from that screen.
Outward from the, yes, from the plane, right? This epipolar plane that we talked about. This, yes, this plane, epipolar plane. So it will go outward. So what will be the dot product of this outward going T cross Q2 with Q2? Here. So this is true, actually true for any cross product and dot product, right? If you have A cross B, and if you do dot product with A, this will be 0 because the angle between these two vectors is 90 degrees, perpendicular. So we have this relation that Q2 times Q2 dot T cross Q2 equal to 0. Now to derive the relationship between Q1 and Q2, we need to express Q2 in terms of Q1. So let's move forward. Now I already gave you the answer. So you can write. So first thing you can write about cross product is that you can express it as a matrix times vector multiplication that we discussed earlier. So you see T cross, so first thing is that Q2 is R equal to RQ1. So Q2, this is equal to rotation of Q1 because the camera has been rotated with the same rotation. That's why the Q1 vector times R is also Q2. Once you have that, we can write T cross this vector by using the matrix notation of T, cross product. Do you remember this thing? We were talking about this when we were discussing cross product is skew symmetric matrix. So this is a skew symmetric matrix. This Tx is a skew symmetric matrix. And the rest remains the same, RQ1 equal to 0. So these are all matrix products now, which is actually the relationship we're looking for. So the relationship is that, Q2 times T cross RQ1 equal to 0 means Q2 transpose TX RQ1 equal to 0. So here you see that the corresponding points in images, there is no single corresponding point, right? There are many corresponding points. Every point, let's say if you're taking a picture, 2 pictures of yourself, then what you have is, let's say your nose point is one corresponding point. Your forehead in those 2 images are another corresponding point. And in the same way, like all the pixels have corresponding points, most of the pixels. But this TX are, they are the same for all the images, for all the pixels in the images. Because the camera has a single rotation and a single translation. The T and R do not change with the pixels. Are you okay with this? Or do you have doubts? So we're looking for a relationship for all the pixels. The T and R are common for all the pixels in the camera. And what we gain is this relationship E equals to TXR. Because this satisfies all the corresponding points, not just this particular corresponding point we're looking for. If we had a different corresponding point, it would still be the same relation. So that's actually a very powerful relation we can use to relate any 2 corresponding points between the images of the same object. And this is what we will use to later on to reconstruct 3D using this epipolar geometry. So some few things about this matrix is that it's a rank 2 matrix. It's not rank 3. It's a 3 by 3 matrix because there's rotation R and TX, both are 3 by 3. And it has 2 equal single values. We talked about single value decompositions, and there were these shearing values, scaling values with the diagonal matrix, and those are the singular values. So can you say why E is rank 2 from this diagram? So let's see what is E times Q1. E times Q1 is a vector whose dot product with Q2 is always 0. So in 3D space, there are many vectors whose dot product is 0, not just 1. Because it can be this way, So let's talk more about these relations. So our relation is Q2 transpose E Q1 equal to 0. Mathematically, its rank is 2, and therefore its determinant is 0. And the two equal single values we talked about can be written in this very complex mathematical formula. You don't need to go into detail of that. This is just a relation that can be used to compute the essential matrix better. So even without this relation, the last relation, you can compute E. So next topic we will see how we can compute E. The reason we want to compute E because let's see this. We had two images and we want to reconstruct 3D. And if we know the location of this camera with respect to this camera, we know that we can draw lines back project into the 3D point, right? But what's happening is that we never know the location of this. Right? Well, I mean, maybe it was 10 meters or 5 meters. We don't know where the camera was. So the reason we want to compute E, because if we compute E, E has the information of R and Tx. So that's why we're doing all this, because we want to get the location of the camera and then get the 3D point. So yes, a lot more mathematics, more equations. So what happens with the real cameras? We studied the real cameras earlier. Let's go back. I think we have time. Yes, after this. So real cameras, we have this. We have this equation. Now K is an invertible matrix, if you see here. So you can just take it to the other side. K inverse. Now, from there we have Q equals to K inverse Q prime. So Q was this coordinate system where UV origin was in the center and there was no focal length. Focal length was 1. Now if you have focal length and the origin is not in the center, the new coordinates is Q prime. This is related to the old coordinate by Q equals to K inverse Q prime. So what it's doing is changing the rays so that your focal length is 1 and your origin is at the center. When you do this, Q equals to K inverse Q prime. So the essential matrix is only valid for Q, not for Q prime. So this looks a bit involved, but what I'm doing is I'm just substituting the value of Q into the original equation here. So you have K inverse Q now, because you can only measure Q prime. You only know the real camera images. You don't know the pinhole camera images. And if you do this, again you will get a relation that is valid for all the images, all the pixels in the images. Because K remains the same for all the images, because focal length doesn't change, and the center of the image plane also doesn't change. So what is changing here is only Q2 prime and Q1 prime. So you get this new relation which is valid for all the pixels in the images, which looks almost exactly same as before. So we represent this new matrix as F, and this is the fundamental matrix. So sorry, there is a mark called too many equations. So for all corresponding points, we have this new relation. So this again has more properties, such as the rank is again 2, and the determinant is 0. So we already discussed about what the rank being 2 means. So now we are very close to what we are going to do tonight in the lab session. So what we are going to do is compute 3D from 2D images. To do that, we will not play with real data, but synthetic data that we will simulate ourselves. And in the next, I think there's one more class after a few days, we will do the real data experiments. So what we're trying to do here is we want to compute the fundamental matrix or the essential matrix. And we have this relation, Q2 prime transpose F Q1 prime equal to 0. In terms of F, if F is a variable, then this is a linear equation, right? But if Q2, Q1 are variables, these are polynomial equations. So this is what you have to see every time when you see equation. People will say polynomial or linear equation, but in terms of what variables? So here, in terms of F variables, as variable, these are still linear equation, if you know Q2 and Q1. And this can be written as this. So F11 is the 1 element, F12 is the first row second column element, and F13 is the first row third column element. So what I want you to do is create this equation yourself as an exercise, because this is what we are going to do in the lab tonight anyway. So just write down, expand this into your equation. So what is Q2 prime? Okay. Yes.